Hello, the purpose of this video is to help you successfully complete experiment number 6. Experiment number 6 covers asymmetrical faults and developing sequence diagrams for systems. The system we are going to analyze is indicated as shown here, and you can see that it has 11 buses and various configurations of generator connections as well as transformer connections. It also shows you in some cases when you have a solidly grounded system for a generator, as shown here, or an ungrounded system or an ungrounded connection, as shown with the deltas on the transformers. So the key parts that you need of this lab is the sequence diagrams for transformers, as well as an understanding of how to build Y-bus, and then how to actually connect the sequence diagrams to build or calculate fault currents. So the first thing we need to do is to draw what our sequence diagrams are going to look like, and I would encourage you to practice this on your own. We're going to draw the positive sequence diagram first, and the positive sequence diagram is the easiest one to draw. For positive sequence, we should only include our power supplies. All other ones should not have power supplies. So if you recall from our discussion during previous videos, we actually show a reference bus and what are the connections to this particular reference bus. Since a positive sequence diagram is a balanced diagram, we have no concerns about how transformers or generators are connected. We'll just have the currents and the voltages being passed through regardless of any connection. So the first one we're going to do, show our generator supply. So this is, we'll just call this G1 since it's connected to bus 1. It'll have its internal impedance here. We're going to run up, and this will be our bus number 1. We're going to go through our transformer impedance. This is bus number 2. Now we're going to branch off into several different directions. So we have an impedance between bus 2 and bus 3. We also will have an impedance between bus 3 and bus 4. Now we're at bus 4, and we can continue in any direction we want. So we'll just go through and we'll actually show the next generator connected through a transformer. So again, ignoring any ground connections for the transformer. This is bus 10. Now we're actually at the other generator, so I'll show the generator impedance and come down with a power supply, and we're at generator 2. So we have a portion of it. Now we can start at any location. Let's just start at bus number 2. And we have an impedance going to bus 5. We have another impedance going to bus 7. And branching off from bus 7, we go through a transformer to bus 11. And then from that transformer, we go to another generator that's connected to G11. So I apologize, it's a little small to see, but you can zoom in this and you can actually see it a little bit better. So now we can continue on from bus 2. So we have a connection here going to bus 6, continuing that connection to bus 8, and then from bus 8 we connect to bus 7, and we are done with that path. We have another path between 3 and 6, and we have one more connection between 6 and bus 4. And so now the final connection we have is between bus 8 and bus 9. And then there is also a connection between bus 4 and bus 9. So that is your positive sequence diagram showing the power supplies and all the impedances that interconnect. To get a sense of what's happening with the interconnections, just know that this is the impedance Z1 to 2. To draw the negative sequence diagram, it equals the positive sequence diagrams. The only difference is we actually subtract the power supplies. those will not be included in our connection diagrams here. So those have no place to show up. So essentially, I'll sort of circle or highlight here which ones those will be turned off, set equal to 0. But because there's no negative sequence data provided in the table, we're going to assume that we have x1 equal x2, so no data. Don't forget these are x values, so when you're setting up your matrices, these should all be multiplied by the j term. Now we have the ability to draw our zero sequence diagram, and I'm going to give myself a slightly bit more room because the zero sequence diagram is a little more difficult to draw. It is very dependent upon the connections that we have to ground. So we'll start off by drawing our reference bus. And at this point, we can actually start to look at our generator connection. So we're going to look at bus 1 again, and we can see at bus 1 in the original figure, we have an impedance associated with it. So we're going to come up through, and we have the impedance associated with the neutral connection. So this is going to be 3 times the xn value there because it's non-zero. And we're also going to have whatever impedance is internal into the generator. Okay? So this one right here would be essentially the x0 value that you would have for generator 1. There's no power supplies, so at this point we can actually show that we have bus 1 at this point. Now we continue on and we see that we have a delta connected transformer, and if you look at your table, no zero sequence current can enter or exit the transformer, so we're going to draw that as an open connection. On the other side, we see that it's a grounded Y, which does allow us to have zero sequence current flow as long as the other side does. Since this is a delta grounded Y, we actually do have an impedance here. And since there's no impedance there, that's just going to be shown as a solid connection. So we come up from our reference, and then this becomes our bus number 2 as shown there. Okay? So now we can continue in doing some of our line data, and our line data does not have any grounding whatsoever, so these are pretty efficient to draw. We have a connection here going to 3, a connection here going to 4. Off of bus 2, we have a connection going to 6, a connection from 3 to 6, and a connection from 4 to 6, all shown there. Continuing on with our transmission line connections, we have a connection between 4 and bus 9. So this is bus 9. And we also have a connection between bus 6, or 9 and 8, I'm sorry. So we'll draw here, and this is bus 8. We have our connection to 6 here. And we have one more transmission system connection, or I should say 2 more. We have one that comes down here and connects to bus 5. And then that continues on and connects to bus 7. And then from 8 and 7, we have a connection as shown here. Now, I'm going to sort of draw this. Let me actually give myself a little more room and draw this over a little bit further to give myself a little more room. Doesn't change any of the results. We're just giving ourselves a little more space to connect our bus 7. So we can see bus 7 is set up very similarly. The transformer is connected very similarly to the transformer between bus 2 and 1. So we come here, we run into our ground. This is the X0. We have an open connection. This is bus 11. And then we have a generator. And we have no 3, 0, but we could put that here. But in this case, you'll notice it is 3 times 0 because the impedance associated with bus, the neutral connection for 11 is 0, so that's going to be 3 times 0. So this again is the x0 value. The final connection we have is bus 4 to bus 10, and that's a YY, so that's just a straight pass-through of the impedance. This is bus 10, and then we drop through our generator impedance, which we have an x0, and then we also include the xn, which is a non-zero value, so we have 3 times xn. So at this point, we have everything we need to go ahead and build our Y buses. I would encourage you to keep in mind that anytime you see you have a bus here, if you have impedances that are in series with each other, you need to add them up first. These impedances here and here are not in series with each other, so they're going to be treated separately. However, these here and here are in series. So if you want to convert those to admittances, it should be done as so. You cannot invert them first and then go ahead and convert those and get the Y buses correctly. So now you have done enough information to go ahead and build your Y buses. You should go ahead and invert. Make a little more room here. We should now invert all impedances to admittances. So if you're sort of following along for a step-by-step process, right, for step 1, what we basically did is we drew our sequence networks, and we'll say positive and negative sequence, and I'll put below here in parentheses, add power supplies to the positive. That way we actually have it drawn correctly. For number 2, we're going to draw the 0 sequence with a keen eye, if you will, for grounding. So this is when I would highlight, use the transformer connection diagrams. This is very important that you use the connection diagrams, because if you don't, you're going to struggle to build these properly. Now at step 3, what we did is we looked at any series impedances and added them together. So add series impedances. And step 4 is to go ahead and invert those impedances to get admittances. And step 5 is we're going to build Y-bus. So we're going to do that on the next slide, and try to help figure out a little bit about how to do that. But because you have an 11 by 11 system, when I'm trying to build this, this is going to get really confusing very quickly. So I'm actually going to go ahead and I'm going to create a spreadsheet essentially that has an 11 by 11 matrix that's going to make it much, much easier to essentially go ahead and lay it out so that it's easier to follow. So we're going to flip to the next page here, and you're going to see how I've got those 11 by 11 matrices set up. Okay, so here is going to be what I would call my Y-bus build, and it's just an 11 by 11 matrix. And because all the J terms, or all the Y buses are going to be, Y elements are going to be J, I'm going to move the J right out front. And to kind of help keep track of things, I'm just going to put the numbers next to this sort of as a housekeeping thing. So I actually know where I am. So I know that if I'm in this column or this location here, I can look at the row and the column indicator, and I can actually say, well, I'm in row 1, comma 1, so I'm looking at the self-admittance, and I'm going to calculate and add up all the admittances for bus 1, 1, or bus 1. And then if I'm in 1, 2, then I'm going to subtract between 1 and 2, etc., etc., etc. So now I would encourage you to pause the video and take a look at the positive and negative sequence diagrams. So you may want to try to do those yourself and take a look and see what you get. But essentially, I'm going to go ahead and draw those or create those now. So at bus 1, 1, or at Y11, I need to sum all the admittances together. So I'm just going to sum y1 plus y12. For 1, 2, I subtract the admittance between bus 1 and 2. There are no other connections between any of the other elements, so these are all going to be zeros. Same thing here. Those are all zeros. And I've got my first row and my first column done. Now I'm going to be at y22, which is the self-admittances, so all the admittances with a 2 in them I have to include. So that's y12 plus y23 plus y25 plus y26. So you can see why it's pretty helpful to have the column set up so it's a little easier to follow. Now I'm going to subtract y23, 0, subtract y25, subtract y26, and the rest are all zeros. And a nice way to check is if you look inside this element here, you can see that you have y12, oops, and I made a mistake. This is a good way to check, right? This is not 0. It's a symmetrical matrix, so I actually should have put y12, and then I start with a 0 here. So you can see by having it set up like this, you can actually help check yourself. There is a y12, so that means I should have subtract the admittance between bus 1 and 2. If it's a self-admittance just connected to the bus 1, then I don't subtract it from any of the buses. So I can see that I have a y23, which means I have a y23 here. So there's a check, a y25 check, and a y26 check, and there's no other elements, so I'm good to go. So again, I have a symmetrical matrix, so this is minus y23, 0, minus y25, minus y26, and the remainders are all zeros. Now I'm on to the y33. So again, just looking at my connection diagram, I have y23 plus y34 plus y36. I see that I have a y34, so I take the negative of the y34. I skip 3,5, take the negative of y36, and there are no other elements, so I have 0 here. I have a symmetrical matrix, and I have 3. So what I'm going to do now is I'm not going to necessarily just discuss, I'm just going to present the entire table and fill it out, and then you can go ahead and check. So I'm going to go ahead and pause the video, but I'm going to actually write in all the data if I can and see if I can get the correct results. Okay, so this is the completed Y-bus matrix for both the positive and negative sequence diagrams. And the only thing that would change here if your negative sequence impedances were different is if you had different numbers. So you would be looking at different numbers. So in that case, and what I did for doing this sort of generically, is if I had a y12, that's the impedance between 1 and 2, but I might either put an underscore -1 to show that's the positive sequence, or if I want to be lazy, I might just show with a 1 added onto it to show that's y1 to 2 with a positive sequence. And so the first few numbers would indicate the bus admittance, and then the last one would indicate if it's positive, negative, or 0 sequence. And so I would encourage you to do something similar to that to go ahead and make it easier for you. So now I'm going to move on to the negative sequence diagram. So again, I encourage you to pause, make sure you understand this process. All right, so here is our negative sequence, our 0 sequence, and just like in the positive and negative sequence, I'm going to go ahead and put some numbering to really make it easy for me to follow along with. And you don't need to do this, I'm just doing it to hopefully make it a little easier for you all to follow. So now you're going to have to look back at your 0 sequence diagram a lot, so I would encourage you to retrieve that and make sure you have it next to you, because you will not be able to do this without looking at the diagram. So as I said before, with your connection from bus 1 to reference, you have the impedance of the generator plus the 3 ZNs. So at this point, it's going to be Y1, but keep in mind that is equal to 1 over the Z0 of the generator plus 3 times the Zn. So those are summed first and then inverted. okay? This is the only case that I'm going to do this for, but keep in mind that you have another generator that has an impedance. So bus 10 is going to have a similar approach to that when you're doing the self-admittance. So just to be aware that when you get to bus 10, you're going to do that. So there's no other connections. It's all, no zero sequence passes through. So the remainder are all zeros. Okay? So we've got the first one done. Now we're going to do the self-admittance. So again, you take a look at the diagram. You see that there is a connection between the transformer and ground. And so that's the impedance between bus 1 and 2, which only connects to the high side of the transformer because, again, it's the Y grounded side of that. So you can take a look at the diagram and you can see where that impedance comes in. So that's Y23. That's the impedance between the two lines or two buses that connect the lines, Y25 plus Y26. This becomes minus Y23, 0 minus Y25 minus Y26, and all the other ones are zeros. So again, I can see here that I have a Y12. Now this is not 100% asymmetric matrix, and that's because there is no connection between bus 1 and 2. So different from the positive and negative sequence diagrams because you actually don't have a connection. This ties to reference. So in effect, this is the same thing as saying this is a self-admittance connected to bus through. It is the transformer impedance that goes to ground. So this is an instance where you don't have a truly symmetrical matrix, but if you recognize the fact that Y12 actually goes to ground, you do see that you have a symmetric matrix because you've got the Y23, 25, and 26. So I've got 23, 25, minus Y26, and then zeros for the remainder of the way. So at this point, I'm going to go ahead and fill in the blanks quickly. You can take a look at your diagram and try to fill out the blocks yourself, which I highly suggest you do that. It will make you way more efficient in actually building these. So next time you hear from me, this diagram should be completely filled in. All right, so here's the final filled in Y bus for the negative sequence diagram. I'm sorry, zero sequence diagram. And now you have enough information to go ahead and continue on. So we are on, at this point, to step 5. We just built our Y buses. Now the next thing we need to do, in both cases, for step 6, is to invert our Y buses to get our Z buses for all 3 diagrams. So you're going to have to invert an 11 by 11 matrix, which may or may not be a trivial amount of work. It's something to consider. Now that we have those, we have enough information to start actually calculating fault currents once we actually build our diagrams. So we're going to look at the 3 different fault types. We'll start off with a single line to ground fault. So if you remember from our discussion in class, a single line to ground fault takes the positive sequence network, the negative sequence network, and the zero sequence network, and connects all 3 of them in series. So let's draw our positive sequence. So this is going to be plus to minus VA1. This is the generator or the Thevenin equivalent voltage seen at any particular bus. And this is the Thevenin equivalent voltage seen for the positive sequence impedance. Then we're going to connect up to the negative sequence, which at this point is only going to have a Thevenin equivalent impedance from bus 2. This is plus to minus VA2. Our current is assumed to go this way and this way. And finally, we'll add our zero sequence. So again, we only have a zero sequence Thevenin equivalent. There's no source. This is plus to minus VA0. Our current is IA0. And then, if we want to include it, we would add 3 times the neutral sequence impedance, whatever that happens to be in our circuit. So to do the single line diagram, now we have enough information to solve for IA0, which is just going to be whatever the Thevenin equivalent voltage is at that circuit or source, divided by our Thevenin equivalent impedance for our positive, plus the Thevenin equivalent impedance for our negative, plus the Thevenin equivalent impedance for our 0, plus whatever the 3Zn happens to be. Once we have the 0 sequence current, we know that 0 equals positive equals negative, because this is just a series circuit, they're all going to be the same. And then we can solve for our voltages. So we see that VA1, our positive sequence, we're just going to do a loop equation around here, is going to be V Thevenin minus Z Thevenin for our positive sequence times IA1 or IA0, they're the same. Our negative sequence voltage, because it's in the opposite direction of the current, is negative Z Thevenin 2 times IA2. And our 0 sequence voltage is going to be negative Z Thevenin 0 times IA0. And now we can substitute those in our matrix. So if we want to solve for VABC, that's just going to be our A matrix times our VA012, and we can do the same thing for our currents and do it in terms of our currents now. And now you have all the fault currents and the fault voltages for a single line to ground fault. Where do you get all these Thevenin equivalent impedances? If you remember, you have our Z bus is going to have a diagonal matrix. These diagonal are all the Z Thevenins seen at each bus. So in row 1, column 1, that's going to be the Thevenin equivalent for bus 1. 2 is bus 2, and on and on and on until we get to bus 11 for this particular problem, for this particular example. So we can actually do all the work and automate it that way and figure out what the values are. That's the single line to ground. Let's move on to the line-to-line fault. And if you recall from class, a line-to-line fault has positive sequence and negative sequence, and they are placed in parallel with each other. So this is E Thevenin. This is going to be Z Thevenin for positive sequence. This is plus to minus VA1, and the current through here is IA1, and then I just connect in parallel that value. Oops, I started to draw that. That's incorrect. I do not have any voltage source. I just have a Thevenin equivalent impedance here with our IA2 and our plus to minus VA2. If you have an impedance in your fault, which oftentimes in a line-to-line and a double line-to-ground you don't, you would just include that here as your fault impedance. So at this point, even though they're in parallel, they're actually just two of them, so they're technically in series. So we're going to solve for IA1 as equal to E Thevenin divided by Z Thevenin 1 plus Z Thevenin 2. We have those. Now we can solve for IA2, and we can see that this is IA1, which is in the opposite direction of IA2, but it's going to be the same value, just in opposite direction, so that is equal to the negative of IA1. And we know that IA0 has to equal 0 because there is no ground fault current, so there wouldn't be any current flow as a result of that. To solve for VA1, that's exactly as the same thing as before. E Thevenin minus IA1 times Z Thevenin 1. Since the two networks are in parallel with each other, if there's no fault impedance, that's also going to be equal to VA2. And exactly what we did before, where we had the symmetrical components, VA0, 1, and 2, IA0, 1, and 2, we can go ahead and calculate our phase, voltages, and currents based on those values. So again, Thevenin impedances are all from the Z bus that you solve for from the Y bus. Let's look at the last fault, which is a line-to-line to ground. So double line to ground fault, same idea. This is E Thevenin at the bus. This is Z Thevenin of the positive sequence. This is plus to minus VA1. This current value is IA1. In parallel with that is the negative sequence, Z Thevenin 2, plus to minus VA2. this current is IA2. And then lastly, we have to include the zero sequence. So that's the difference between the line-to-line and double line-to-ground fault. We just have Z Thevenin 0 here, plus to minus VA 0 and IA 0. Now at this point, it depends on how you do it, but again, if I want to solve for IA1, it's going to be E Thevenin divided by Z Thevenin 1 plus the parallel combination because the two impedances are in parallel with each other. So we could do that and solve for it. The next step, there's a bunch of different ways to do it, but probably the easiest way is to solve for VA1, and that's going to be equal to E Thevenin minus IA1 times Z Thevenin 1, which that happens to equal VA2, and that also happens to equal VA0 because, again, they're in parallel with each other. Once you have VA2 and VA0, then you can just simply solve for IA2, which IA2 is going to be equal to the negative, because it's in the opposite direction of the voltage drop, VA2 divided by Z Thevenin 2. And IA0 is going to be equal to the negative of VA0 over Z Thevenin 0. So now we have our symmetrical voltages and components. We can go ahead very quickly and calculate what our phase components are going to be and back calculate from there. So we can do all those elements. The only one that we haven't talked about, but it's technically not a symmetrical fault, is a three-phase fault. So if we do a three-phase fault, this is really easy. A three-phase fault is going to be E Thevenin at the bus divided by our Z Thevenin 1. And this is plus to minus VA1. So essentially what we're saying there is if you really want to just solve for the positive sequence current, because IA2 is going to equal IA0, which is going to equal 0, because in a balanced three-phase fault, we don't have negative or zero sequence. So you can pull out the Z-bus parameters and calculate what those values need to be, and it makes it very, very simple to do that. So once we have all that information, we've got our networks. Now we can do step 7, which is calculate the faults. And you have to just do that 11 times times 3, right? Because you have a single line-to-ground fault, line-to-line fault, and a double line-to-ground fault. You can also check if you want to do it for the three-phase fault, but you're going to have 11 buses where you have to look at these Thevenin equivalent impedances and voltages. You can assume one at an angle of 0 for your Thevenin equivalent voltages. Assume that the system is initially unloaded, and you can get some pretty darn good results that way. And then your last step for this lab is find the max fault current. And then write it up. I have completed a MATLAB script file that I'll make available to you. It gets a little lengthy, but I also sort of automate the process of calculating these faults. I do them with some while loops. You don't need to necessarily do that. You can do it by hand, whatever you want, but I'll show you that MATLAB script in a moment. And here's my MATLAB script. So I included a fault impedance, but you actually don't need to include that. You can ignore that. You can set that equal to 0. And that only affects not the Z-bus calculations. That's just going to affect the fault current calculations. And so you'll notice I have my A, 1 at an angle of 20, my major A matrix that I encourage you to memorize in your calculator. And then I actually specified all the positive sequence. So you notice that I have a 1 all at the end here. These are the positive sequence admittances. So those are all defined here. And then next to those I have those negative zero sequence admittances. And notice at bus 1 as well as bus 10, I added those admittances together, right? Those admittances were added together before they were inverted. The rest of them I just added it as normal. But again, I denoted that it was a zero sequence except for the case where I had bus connections, and I showed them that way. And then this is positive and negative sequence Y bus, and then I invert it. And then I have my 0 sequence. And so you can go ahead and check those, but they should be consistent with the 2 tables that I provided earlier. Then I did my 3-phase fault calculation. So I just did a for loop, and I went through the number of buses, 11 in this case, and then I just divided the 1 at an angle of 0 divided by the Thevenin equivalent, and I pulled out the max fault current. And then I just did some display stuff that you may or may not decide to do. I did the same thing for single line to ground. So if you remember, I solved for the IA0 or IA1 or IA2. They're all the same by taking the pre-fault voltage, again, 1 at an angle of 0, and I sum all the Thevenin equivalent impedances there. And then I set them equal to 0. I set them equal to each other, and then I just pull out my current. And then I just do some quick ways of going ahead and pulling that out. Then I do the line-to-line fault. So again, those only have the positive and negative sequence values. So I solve for a positive sequence, negative sequence is the opposite. Then I substitute in my A matrix. You will notice that I forced in the 0 there because it needs to be a 3x1 matrix. So I've got that in there, and then I figured out that value as well. And then finally, for the double line to ground, I've got my positive sequence, and then these two are in parallel, right? It's the 1 over the 1 over plus, added them together, and then that's how I inverted them. And then these two are slightly different calculated. Essentially all I did there was I just used KCL. So if you remember from our networks, we have network, 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 those currents. These are in parallel with each other. So I just did basically current divider to go ahead and solve for those. So that's another way to do it, and I'm just giving you a bunch of different options to do that. And then I spit through all those, continue on, and then I display the max 3-phase fault current, which is 8.5 per unit and occurs at bus 10. The single line to ground is 8.4, which occurs at bus 2. The maximum line is 7.3 and occurs at bus 10. And double line to ground is 8.14 and occurs at bus 10. So as I've discussed in class, what you'll see is the 3 line is the worst. The second worst is single line to ground, and then it's, who cares about these unless you're looking for distance. Usually the line to line fault is the minimum. So this usually is the min, and this is almost always the max, but on occasion you'll see the single line to ground fault being the max. So that's it for the lab. I hope you found this discussion or description of how to perform Lab 6 helpful. And please feel free to give me any comments or feedbacks of how I can make this better. Thank you very much.